Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. It's my great pleasure to welcome old friend, Professor Wen Gao, and a new friend, Zhongxuan Luo, to MSR. So we have two talks, and we'll start with Wen's talk. So Wen is a professor at Beijing University and a member of Chinese Academy of Engineering, and very recently he's a vice president of NSF China, not NSF US, okay, NSF China. So he's a bigger figure in China, and he was president of Institute of Computing, Chinese Academy of Science, and also vice president of the Graduate School of Chinese Academy of Science. So the long title, I won't take too long. So he has been doing a lot of work in video coding, and he will talk about some new research topic and also some standardization effort. One, please.
Thank you. Thanks, Zheng Yu, invited me to be here. So today I want to share with you about video coding and some new direction, maybe not new direction, some new stuff. All the direction, but get some new stuff about the video coding. Use the model-based. And there is a showcase in this year in the June. We published IEEE standard, which use the new model. So I will talk a little bit about the scoop and the key result about that standard, then the summary. So I think video coding basically is the technology try to remove the redundancy from video sequences. So think about how many or kind of different redundancy we can remove. Basically, we can think about three kind of redundancy. One is temporal redundancy, another is a spatial, and the third one actually is, we call that a coding redundancy. So the system, the standard system, just mix this three kind of technology into together to make the system. So because you use multiply technology, so the system normally called a hybrid video coding system. So current system basically use the results, the video in, then so first part use the transform technique to remove the temporal, the spatial redundancy. Then there's a loop, try to remove the motion-related redundancy. We call that temporal redundancy. Then last one, there's entropy coding, try to remove the coding redundancy. So this is the first generation, second generation, and the third generation of video coding standard flowchart. So whatever H.26 plus X or MPEG-X or some new standard, actually all the flowchart looks like quite same. So the top one actually is the transform coding, and the bottom one is prediction coding, try to remove the temporal redundancy, and the entropy coding used for code the sequences more efficiently. So this is the state of art for today's coding technology. So video coding has made a big impact to TV industry, because for TV industry, in the early time is standard TV, and then later on HD TV. 3 years ago, 3D TV. From this year, the Ultra HD TV. So I think the video coding technology is the base for this progressive. So with the technology, the coding ratio, the coding efficiency start from 50 to 1 compress ratio. Right now is around 225. Sometimes we said around 300. Then next generation should be something like 450 to 1 compression ratio. So, but if we think about what's the upper bound for this technology, then we can, later on I will explain, the upper bound should be very high. So today's the state of art only reach quite low, the result. So we still have quite, big room to do some new research. For understand the upper bound, so we can think about 2D matrix transform. For example, give input matrix. This is the HD sequences, one frame of sequences. So the resolution is 1920 by 1080. So then we can simply put some zero, then to make a square matrix. So then if we can find a transform to make this success, then the Y become only element here is non-zero, other all zero. So with this transform, it's very clear we can make very efficient compress. So actually this one is exist. So one of them is SVD. Then if think about in 3D dimension the sequences, then the upper bound should be much higher than that, because normally when we do video coding, we can use at least 15 frames for one group of picture. Sometimes we can use 60, and if we think about the much longer the sequences, then we can make much higher the upper bound of transform the compression. So this is the idea how we can make the in 3D dimension in longer sequences of video. With that, we can make much higher the 3D matrix transform. So the data looks like today. From start is in 1994 year of 1994. This is the first generation. Then I think this is the second generation, which finished in 2003. Today, I think most systems use MPEG-4 or H.264. This is the second generation. Then in this year, actually there's a new standard finished called MPEG HEVC or H.265. So which, if we look at in the HD resolution level, is around 300 to 1 compression ratio. Then what's the next? So if we look at the roadmap, next generation of video coding should be compression ratio in 600 to 1 for HD resolution. Of course, maybe 10 years later, HD resolution is too low, maybe is UHD. So the compression will be a little bit higher than 600 to 1. So here is the, this is standard TV cooperation, the standard TV compress ratio. So there is a even the standard is now changed, but the compression ratio get a little bit better. little bit better with time being, such as in the MPEG-2 time, start for SD resolution, the compression ratio, for one SD channel is about 5 megabit per channel. But with time being in today, we can use similar technology. We can use about 1.5 to 2 megabit to compress the same quality of the video. So this is the progressive by the optimization of encoder. It is not a contribution from standard, but it's a contribution from encoder optimization technology. So people try to make more higher compression, standard by using some technology. So one technology actually people try to use, the big block of data. For example, in the early time, only 2 types of block of data be used for transform or for prediction. But with time being, for example, in the third generation, there's a lot of different type of block be used for the for get higher coding efficiency. For example, 60 by 64 by 64 down to 32 by 32 and down to 16 by 16 and down to 8 by 8. So with a lot of different combination, so you can find the right block to use. That's for transform. For prediction, for motion estimation and so on, we can use very tiny prediction by different direction. Early time, only 4 direction we can measure it is match or not. Then in the second generation, the direction from 4 go to 9. And in third generation, actually the direction go to much more. It's 33, maybe 32, maybe 36, and so on. So with a lot of direction, then you can hit even you can match that. So which can save the bits. So this is the overall the transform and the prediction. So for the data structure, we can use figure like this. So there's big block and small block down to a very, very small block, and also with different combination. So this is the basic idea. First generation, second generation, third generation video coding technology has been used. But if we look at the detail for the technology, it must be something missed. So there is one thing, if we look at, one stuff is today's video coding standard mostly is targeted on TV industry, on TV broadcasting and so on. So by that, there is a lot of limitation for that industry. So this technology actually has been used for, simply used for video, for surveillance video, and for internet video. So this is not a good thing because the TV industry has a lot of special, thing needed to make their requirement, to match their requirement. For example, they count the clock very accurate. So if you delay even one clock, then the system will be crashed. So that is why the frame rate is a very important thing. So you cannot change frame rate during the encoding process or decoding process. So if you want to change the frame rate, you need a restart. So that is why use this technology for internet video is not efficient. So of course today's internet video coding algorithm has made a lot of change, but it's not standard. It's a local or it's a private feature. And for another missing is for video surveillance. Surveillance video actually is very unique. So use this technology for that is also not efficient. So that is why we try to look at a different application, try to use different technology combination to make a much better system for the special application. Of course, people very easy to think maybe we can use some vision-based coding, which it should be much efficient. So in last 40, 50 years, people working in that direction spend a lot of time and energy, but the result is not good because of today, the video coding standard now use this kind of technology yet. So, but a lot of research results already there. So we can use the idea for the application like internet coding, video coding, and surveillance video coding. Okay, so there's another factor. Normally people want to write paper. We were mentioned as the perceptual coding. Because when you code video, there's distortion. So with same distortion, which solution is the best for quality? So people can argue maybe we can measure the distortion by PSNR. The result is not good. Maybe we can measure that by some metrics. So eventually people think maybe because all the compressed video after decoding is looked at by human's eye. So humans, reaction for the quality is more important. So this direction is the perceptual coding. So with that, also a lot of research has been done. So this result partly has been integrated into the coding system today. So that is about the video coding. Then why model-based? So after explain why it's not good to use the TV-oriented coding standard for internet video and for surveillance video. So of course, we can think a different way for surveillance video, for example. Then if we look at what research has been done for the model-based coding, there's a lot of good work has been done. For example, people has been working in geometric partition for help the coding. For example, can use the triangle or use the mesh network to describe the surface and so on. So I think later on, Professor Luo maybe mention some part about that, but of course not for coding, but for image processing. So this is one direction people has been done. The second one is very clear from a computer vision point of view. If can use good segmentation, use that information, then help the video coding also is a good idea. Of course, a lot of research has been done. But the question is, do you have a stable segmentation algorithm for coding, which don't need people in the loop? So this is the question. Then the third one is the object-based coding. I think this item is very easy to understand. And then is the knowledge-based coding. Even we said knowledge-based actually is the vision analysis and synthesis. So basically, this direction of research is focused on the face-related or talking head-related. So people try to modeling the face expression or talking face itself, face motion, and use that to save the beats. There's also related a little bit higher layer than the knowledge-based, is a semantic-based coding. So which not only to describe the surface itself, also for the moment, for the face moment, can use the semantic-based technology. Then the sixth one actually is something I mentioned for visual system, human visual system related, which use the perceptual coding idea. Then the last one actually is quite new direction. It's a learning-based coding. So use the data in the internet, in the cloud, use more data, get more knowledge, use that knowledge to support the good coding algorithm. So this direction has been looked at as a very important thing because the big data, if you look at the partition of big data, over 80% of data is image and video. And especially if you look at the video part, the surveillance video is the majority in the big data. Maybe about 40–50% of the data is surveillance video data. So for this kind of data, if we can find a good compression algorithm, then we can save the storage or can save the transmission cost. Of course, surveillance video also make a special requirement for what kind of quality you need protect for further pattern recognition. We have found out in most systems today used in the surveillance video, they use quite a higher compress ratio. It's much higher than the coding standard used in TV industry. The only reason is they try to save the cost of storage, but it is not good because after you compressed, then if you want to find something, find some special people, find some object from the surveillance video, you'll find out it's very hard to do that because you have after the high compress ratio compress, you have lose a lot of feature. Then you cannot figure out what's the correct result. For example, of course, the resolution is another issue. For face recognition, if the quality of resolution is too low, then it is not easy to find the people, the object. Of course, for make a better pattern recognition, you need a very high resolution. The resolution is much higher than today's system has been used. Another issue actually is for video, surveillance video, normally, a compress is not the only target. The target is compress first, then later on should be do analysis, the behavior or the people's behavior or who is that. So, but today the video coding stuff is only for make high resolution, high compression ratio, but for video content analysis job, they do in separately. So none of the system is considered two things together. So just like the railway, it is parallel in all the way. So it's not good. So one of the reasons is all the coding standard only think about how to code the video sequences inefficient, not how to analyze the video efficient. So we try to make some combination, make a standard which can take care of two stuff. Okay, so if we can do that, there's a very direct thinking. Maybe we can get much higher compress ratio by, use a model, use a background, foreground model, which should be, get a higher coding efficient. Then later on, since we have the background and foreground, then for the foreground is related to the object. So for that, you can make the analysis, the project, the task make it much easier. So that is the one thing we try to, put together. So as I mentioned, for the quality, the resolution of the image is related to the pattern recognition accuracy. For example, if so here is the face recognition ratio. So this is the compress, how hard you compress the data. So normally the parameter in the video coding, we normally use the QP to describe the how hard you have compressed the data. So the big QP means much higher compression ratio. So if you look at that, you can find out basically maybe QP equal to 10. Here you can get 90% and up recognition ratio. But with the QP get bigger, so the compression ratio get down very fast. So that's why we should understand if you want to make the analysis more accurate, you cannot compress too much to everything. So the idea is maybe you can compress the object much less, and then you can compress the background much higher. Then overall it is okay. So that's the idea for how we can compress surveillance video for that. Okay, so with this idea, then what's the showcase we have done in IEEE Standards Association. So the IEEE 1857 is a working group we initialized in last year, actually with one in the year. Let me see. So in the year 2011, so we basically initialized the working group. Then the working group officially start work in last year in February 15. So I am the chair, and there's a vice chair and secretary. Then actually after 1 year work, this standard has been finished. So this is all the process we have done to make this standard. Is also the process. So this is the publication documentation for this standard. So basically, a lot of authors involved in this product in this standard. So this standard cover different things. Can cover basically there's we call the make group or make profile. It's a basic profile. Then up on the make profile, there's a profile for special application. For example, there's an enhanced profile which is special for HD movie application. So there is a mobile profile for mobile application. There is a surveillance profile. There's two actually layer. One is a baseline layer, another is we call the S2 layer, a higher layer. So this layer is more efficient for surveillance video coding. So this standard, the standard IEEE 1815 is the video surveillance profile. There's a definition about the parameter how you can coding the surveillance video. Within that, there's some parameter is very important. For example, there's a region ID. So there's a region number. So how many region you want to make it as interesting region of interesting. So if there's a 2 region, then the number is 2. Then for the number of region, each region you can describe for where is start, where is end, and which parameter you have been used. Later on, you can base on that to make the object behavior analysis or the tracking and so on. Also, for this standard can support the camera, many camera parameter, such as the camera data can be location, direction, and so on. Also, can integrate many useful information like GPS information. So before this time, each time if you want to make a search, use multiple camera video, then you need have a system to figure out which data is captured from where. But with this information, it is very natural. So you know where is the camera mounted at, because there's a GPS information there. So the kernel technology for video surveillance video coding actually is model-based. Basic idea is, there's an original frame. Then from the sequences, actually, we can calculate a background. If we can make the background very good, then we can figure out, after differential, we can figure out where is the foreground. So the foreground, actually, we can use that for more efficient coding and for analysis. Of course, in the coding structure, we can have a switch. The switch can, use just the original video scheme, or can use the background, the foreground video coding scheme. Also, we can, support not only the fixed region of the camera. Also, the camera can be rotated, can zoom in, zoom out. For that, the background model is a little bit complicated to build up. And for surveillance video, also the condition will be changed for lighting, weather, and so on. So also we have some higher layer parameter set for descript in the different condition of the video caption. So here's the basic idea how we can make the background. So if you look at it, there's a white line here. So this is the line. This is the the plan we have this show here. But basically we have changed the data structure from original data structure. In original, normally is left view is X, Y. Z is timing in timing zone. So X, Y, Z. But we turn that in a view Z, Y, X. So this is the Z, Y, X view. So you look at here, you can find out it's much clean than left one. So this is much easier for make the model, for background model. So basically, all calculation to to make the background model is on this plan and this space. Okay. So this is the algorithm we have used for that. So here is the original sequences. We call the training frames. Then by this training frame, we can look at it in this direction. So not this direction. We can cut in this one and look at it in this direction. So just like this. So we turn that as square. Then based on that, we can make the model update. So if you want to now the detail how that work, we have published several papers about that. So I can give you the paper. So this is the result we have done, by that algorithm. So this is the first. Sorry, that's something right in Chinese. The first frame, and this is the frame of 118. So this is the result. So if you look at that, so the result is not that clean. Something still remains there, but most of the object has been removed. So this is the background, and this is the original one. So you can make the difference. Then you can do, you can figure out the foreground. So the algorithm is just look like. So you get the sequences. Then you can have the background. Then you can have the foreground. Then you can coding background and foreground separate in different sequences. Then make that more efficient. Okay. So this is the format we have been used in IEEE 1857. Then with that, we can easily to figure out the region of interest. Of course, the object is quite sometimes it's tiny and small. Then we can use algorithm to make that more in a little bit larger region, which is easy to deal with for decoding. So for that, we can use that for real-time online surveillance video coding. Also, in most today's system, for example, HDF 264 already there. Then we can use offline process to use transcoding, which also make a very efficient result for storage and for later on analysis. Okay, so we have used this system to recommend video surveillance system, which, for example, by that we can record video sequences. Then, of course, with the foreground, we can just keep this region in very less compressed, so which later on you can do face recognition more accurate. Also can use this structure to support the human behavior analysis. So there's a high layer event. So with region, then we can get the object layer. Then we can make a much higher layer in event layer, which is mostly multi-frame put together to make the behavior description. So this standard actually can support, if you want to do the video analysis, then can support in 3 layers. The top layer we call the index layer. So by index layer, actually, it's very easy for later on retrieval, analysis, and so on. Then we can have the object layer. For object layer is a foreground layer. Okay. Also, we can have the orange layer. We call that bit stream layer. Is just like traditional process. So then some people ask, is this model only work in IEEE 1857? We said no. So 2 of my students has done a quite good experiment to use the model-based algorithm over HEVC. So the result is we change nothing, just put foreground, background model there. Then here is the bit saving. So we saving 44.78% of a bit than HEVC with similar quality, similar video quality. That means we almost double the performance than HEVC. This is for, of course, for surveillance video. So my student also done same experiment on conference video. Maybe I think Zheng, you're more interested into this one. The result is not that impressive because it's only saving 13.79% of a bit compared to HEVC. Of course, one of the reasons is, for this one, the background region is a majority. So you can make a more efficient one. But for this one, for conference video, majority actually is a human face. So when you move, when you change, it's change. So you cannot make much background to make the advantage. Okay, so this is the first stage we already done. Then we have our next step. So the roadmap looks like today we have finished the 1857 2013. The next year we plan to make version 2. So version 2, so AVS 2 is from the performance point of view is equivalent to HEVC. So I believe next year for video surveillance we can have IEEE 1857 double the coding efficiency than HEVC on surveillance video application. We also have the audio part, system part, and then this one is quite unique. We have we call that description part, which can support the analysis and synthesis later on. And we also have the interface part. Okay, so this is the major part I want to share with you. For the summary, I have two parts. One is the future direction. So basically, today's video coding use the block-based technology, so make the coding efficiency improvement. Then what I'm talking as the model-based is somehow belong to the knowledge-based. Then there's one direction I did not touch is the cloud-based, use more data to learning-based and so on. So I didn't talk here. And there's also one thing I didn't touch is the perceptive coding, which also some people working on. Of course, in this stage, quite many papers already published, but only a very few technology integrated in this standard. So I think people will keeping their effort on make the video coding efficiency higher and higher and higher. Of course, we should not only look at the broadcasting video coding standard, we also need to look at the surveillance video and the internet video. So we have published some paper related to the model-based coding. So if you are interested, I can give you the list. So before I finish my talk, I think as Zheng mentioned, from this year I have a new job, the job in NSF China. So NSF China is quite young, so I will introduce a little bit about that. It's relatively young. It's start in 1986. So I think the mission is quite close to the NSF in United States. So this is the organization structure we have now today. So basically, we have 8 departments for different area. So the area 6 is information science. So I'm in charge of this one. Also, there is an office. So the general office, the planning office, and so on. So the third one is science policy office. So I'm in charge of this office already. So there's some other. So the funding basically supports 3 things. One is research, one is support people, And the third one is support to environment, research environment. So people, we have quite a different category of funding to support young people, junior, senior, junior people, and senior people, and so on. So we have different category. For project also, for the research also we have different program, general program, key program, major research plan, and so on. So of course for the so for the people there's different category has to be matched in different level old. So for the funding, there are program category, there are general, key, and so on. Also for the money, for the amount of support, from some 100K, from some 10K, 40K, and so on, and to $500,000 RMB. $500,000 US dollars. So the RMB is in the private one. So for the total budget by year, so you can see from start the NSFC, the funding is not that many, but with time being, it's grow up quite fast. Also, it's one of these things you can, connect with Chinese economy growing. For the number of proposal, the application, actually last year is going to the top. Is 170,000 proposal full year come to the NSFC. But this year a little bit down because we have a new policy. So each people, if fail 2 years, has to be stopped 1 year in application. So which somebody apply 2 times, fail, stop. Somebody apply 1 year, they automatically stop 1 year and try next year. They think maybe they need to get more good preparation than do the application. So for the evaluation process, basically after the proposal coming into the NSFC, then actually we don't accept the proposal from person. We accept, we collect from institution. So any faculty need to give the proposal to their institution. Then we collect the proposal from institution. Then which we're going to different direction, different division or department. Then there's the format review. If the format not match, so we're not going to the review process. So there are totally 5% of proposal is format is not good. Then after that there's a peer review. So peer review will select the 35% from 95, then go to the panel review. Then after panel review, around 20% proposal will be accepted. Then we'll get the support. So I think that's the overall the process of SFC. Thank you very much.
Okay, thank you.